Thank you so much for attending, all of you. Welcome. So as I was telling you before the beginning of this webinar, which is only going to be 1 hour, right? We're going to talk about beamforming. How is beamforming used in 5G? We're going to talk about the types of beamforming, that is digital and analog, and the main differences between them. And as you should know, there's also a combination of both of them, digital and analog, and this is called, of course, hybrid beamforming. We're also going to tell you everything about massive MIMO. Massive MIMO, my friends, in short, is just a collection of large antenna elements or large subarrays, okay? We're also going to tell you how you can use them in case of single-user MIMO or multi-user MIMO. I'll try to color the presentation with a few practical examples. For instance, I'll tell you how many beams are being used in frequency range 1 in 5G and in frequency range 2. We're also going to be talking about how these beams are used. In particular, you should know that in 5G we use some of those beams for coverage. They're also known as coverage beams or SS, synchronization signal block beams, right? But we also have some narrower beams, and they are known as traffic beams. These traffic beams help me deliver my data to my subscribers. Beamforming is the method used for 5G to deliver data to my subscribers. And you can start thinking as a beam as a spotlight in a concert venue, right? Rather than having one light covering the entire stage with a given beam or giant light, right? We use several spotlights in order to increase my signer when we deliver data to my subscribers, okay? We're also going to talk about the possibility of using beamforming in low range, in frequency range 1. Frequency range 1 is frequencies of operation below 7 gigahertz. Or we're also going to tell you, right, beamforming operation. Is there a handover between beams, Lauro? No. What do we do? Beam switching. Do we do this via layer 3? Do we do beam switching via layer 3? Well, in theory, you shouldn't, right? You should be using the MAC control element or layer 2, right? You do beam switching via layer 2. That is, there is no handover. We just tell the UE, don't listen to this beam, now go and listen to this beam, right? I'm going to tell you how we select the beam, the coverage beam, and then how we get data in the traffic beams, and how this beam switching gets done. Also, you will tell me, Laura, but how do we pick the beam originally? Right, beam selection in 5G is mapped to your RACH procedure, okay? We're going to go through this. All right, here we go. So, these are the objectives, guys, which I already told you. So we're going to move faster so that you get more information about this. All right, so beamforming. All right, so if you went to high school, which is probably what I did, no, it wasn't in high school, they told you about beamforming, particularly if you're an electrical engineer, right? Your teacher told you, hey, get a dipole, connect it, and walk around, measure the received power, and get the antenna radiation pattern. Right, let's go and try to see what the beam of this antenna is, right? Or what the coverage of this antenna is. So beamforming, amigos, is nothing else than sending or radiating energy in a given direction so that, for example, if we have two antenna elements, right? Two antenna elements in here, by modifying the amplitude and the phase that we inject to two antenna elements, we can send, right, this given signal in a given direction. So if we want to create a given beam in this direction, we're going to modify the amplitude and the phase of my symbols such that in this direction where my subscriber is, right, there you go, Granky. That's Grandma with her motorcycle. If we want to send the data in this direction and maximize the amplitude of the signal in that point, then we're going to select the amplitude and phases that we are feeding my antenna elements with such that the amplitude or the symbols add constructively. As you can imagine, there's going to be other places. For example, here, where there will not be signal or the signal will be minimized. So you can think it both ways. You can say, oh, I'm maximizing the energy in a given direction by modifying the amplitude and the phase of my two symbols in my two antenna elements, right? I'm maximizing my signal. Or you can also say, I am minimizing the interference in other places, right? So this is just the general idea. Do we need to plan different Raj root sequence index for every beam? Ah, very good. We'll talk about these Sheikh in a little bit when we get to the Raj. Very good question. Okay, so that's the general concept of beamforming. So Lauro, do we use beamforming in 5G? Yes, was it already proposed in LTE? Yes, but nobody used it. Now in 5G, you're going to see that these beams are actually not created only horizontally, right? Beam here, beam here, beam here, beam here, but we also create them vertically. In other words, guys, you're going to have subarrays, which is subarrays are a collection of antenna elements, right? So I'm going to put in here, for example, nine subarrays, and these subarrays are going to create beams, right, in the horizontal plane, but we're also going to be creating beams on the vertical plane. So you can ask your vendors to give you their antenna radiation pattern, and you will see how we will have horizontal and vertical beams, okay? So in the past, in LTE, we used to have this giant beam that has this radiation pattern, right, in the horizontal plane, but also on the vertical plane, and that covered everything. In 5G, we're going to have antenna subarrays, and each subarray you can dedicate it for the horizontal plane, but also on the vertical plane. So we can cover horizontally, but also vertically, okay? So this is called full dimension MIMO, in which we can cover both horizontal and vertically. All right, so in order for you to understand this beamforming, I went ahead and created a few drawings so that we could move faster. So let us assume that you have an LTE network, right? Let's assume that you have an LTE network and that you have a radome. You have a radome. So this radome, guys, would have, let's say that you go and deploy your radome in the AWS band. Right? You go and deploy an AWS band. I told you that in order to create beamforming, you need antenna elements, right? So in this case, assume that we have the following antenna elements. I'm going to draw them, right? This is antenna element, the yellow one, antenna element. We have 4 antenna elements for my first subarray. And this antenna element, the yellow ones, amigos, are connected to, let's say, port number 2. We're also going to have, let's say, four more antenna elements that are cross-polarized, meaning they're using another polarization. I'll explain this in a minute. So these orange ones are going to be connected to port number 1. So there you go, we have 2 antennas now. Likewise, we can go and create other subarrays in here, the green ones. So these are going to be connected to port number 3. And finally, we will have the blue ones, which are cross-polarized at 45 degrees. So these blue ones, the blue ones are 4 antenna elements, and they're using linear polarization with 45 degrees, right? 45 degrees polarization. The green ones are cross-polarized, linear polarization, but actually that's a 45 degrees, right? The green ones is 45 degrees, and the blue ones are negative 45 degrees. They are linear polarization. Each of these antenna elements, the yellow ones, the subarray, the yellow subarray, is going to create a beam cross-polarized, right? So this is going to be a given beam, like that. The yellow ones. The orange ones are cross-polarized, meaning that they're going to be creating a beam that would look something like this, guys, right? It goes in the vertical domain, like that. Right? You see, they're cross-polarized. Can we do cross cabling and any gain with cross cabling and linear cabling? Can we do cross cabling? I'm not understanding very well your question, Kushwant, but let me see if I answer your question as we go. Right? So in this case, we have 4 beams, right? 4 beams. You see it, guys? We have 4 beams. They are cross-polarized. So what is single user MIMO, Lauro? In single user MIMO, let us assume that you have a subscriber. In this case, I'm putting a person with a motorcycle, right? In this case, this person is downloading a file from the internet, and we have four subarrays: port 1, port 2, port 3, and port 4. You know that each of these subarrays are going to be creating a beam. Now, we are assuming that my subscriber has 4 receiving antennas. I'm going to be sending one layer of data, that in this case, 1 packet, right? Let's say that I'm going to be sending packet number 1 in antenna 1 or subarray 1, port 1. I'm going to be sending packet 2 of this file that this person is downloading from the internet in antenna 2, port 2, subarray 2, which is cross-polarized. Then we're going to be using packet number 3 in antenna 3, subarray 3, port 3, okay? And finally, packet number 4, we're going to be sending it from the 4th antenna or subarray, okay? Now, pay attention. All of these beams are using the same resource blocks, right? Resource blocks 10 to 20, 10 to 20, 10 to 20, 10 to 20 at the same time, but they're using a different code. Get it? So we're sending up to 4 times more information than in transmit diversity or with a single antenna, right? So we have a gain of 4 because we are creating 4 beams, right? So as you remember, we have the orange beam, which is covering the subscriber. We also are using the yellow beam. Now we have the orange beam. Then we're going to have the blue beam. Remember, some of them are cross-polarized. And finally, we have the green beam. There you go. This is also known as single-user MIMO. The advantage of single-user MIMO is that we increase the user throughput, okay? How do we get this, Lauro? Oh, we get this because we're using some sort of beamforming in this case, which is also MIMO. And this is typically for lower bands, right? Bands of operation below 3 gigahertz, okay? There is also another technique called, right? So this one was my single user MIMO, where we use several subarrays for one single subscriber. What's the difference between, okay, the beams should be 90 degrees apart as the antennas are cross-polarized. Yes, they are, right? 45 degrees and negative 45. So the beams are 45 degrees apart, right, like that. What we are doing, guys, is the vertical field and the magnetic field are 90 degrees, right, separated. So if this is my electrical field, it's a 45 degrees, and this is the other one, negative 45, so they are 90 degrees apart. Okay, what exactly is massive MIMO? Massive MIMO is nothing else than a collection of large antenna elements. I'm going to come back to this in a bit, okay? When you have a large collection of antenna elements, then you're going to use massive MIMO. I'll come back to this, don't you worry. Now, when we use beamforming for multi-user MIMO, how does that work, Lauro? So in that particular case, let us go and explain to you what multi-user MIMO is. Let us assume that we have a large collection of antennas, right? A large collection of antennas. And we have several subarrays. Let's go back a little bit and try to explain this in more detail. Okay. In 5G, the frequencies of operation have been divided into frequency range 1 below 7 gigahertz and frequency range 2 above 7 gigahertz. In frequency range 1, they went and also created two sub-bands, right? We have the low band. Low band means that my frequencies of operation are below 3 gigahertz. And we also have my mid band. My mid band are frequencies of operation between 3 gigahertz and 7 gigahertz. Okay, frequency range 2 is above 7 gigahertz. Now, let's just go back a tiny bit because I think the concept was not clear. So when you deploy your antennas, when you want to deploy your antennas in low band, because of the frequency of operation, the size of my of my antenna elements is big. The size of these radomes, of these antenna elements, right, is half lambda. So when you work on frequencies of operation, let's say of 1 gigahertz, the size, the lambda, is about 30 centimeters. We want to put these antenna elements at lambda by 2. So in the case of 1 gigahertz, this antenna elements is about 15 centimeters. So if you think about this, and they have to be separated by lambda by 2, right? So when you think about this, if I want to put antenna elements in a radome, maybe I can only put 4, and more than likely they will be the size of that door back there, right? So there's huge radomes at 1 gigahertz, and they get bigger at 700 or 600 megahertz. So as you can see, I cannot put that many antenna elements there. So there you go, right? So in this case, in low bands, we have to have these giant radomes, and they typically do not contain that many antenna elements. However, as we increase the frequencies of operation, my lambda decreases. So if at 1 gigahertz you have an antenna element of 15 centimeters, lambda by 2, at 2 gigahertz they're going to be 7.5 centimeters, and so on. So as you increase the frequencies of operation, if you keep the size of your radome constant, then you can have more antenna elements, okay? So in frequency range 2, you can find subarrays, right? A subarray is just a collection of antenna elements. You can have subarrays of, let's say, 256 by 256. So in this case, we have this giant radome. We have this giant radome in which we have 1,024 antenna elements. Why? Because the frequency of operation is larger, the antenna elements are smaller, and I can group them. In this case, I have 1,024 antenna elements, but I decided to group them into 4 subarrays. Lauro, so what happens with these subarrays? Each subarray can produce a beam, right? For example, in this case, I will be producing 4 beams. So Laura, is there a relationship between the number of antenna elements and the number and the beam width and the beam gain? Yes. The more antenna elements you have in a given subarray, the smaller the beam and the larger the gain. Again, the more antenna elements you have in a given subarray, the larger the antenna gain, or the greater the antenna gain, and the smaller the beam width, okay? Right, so if we keep showing you more examples, right? In this case, I have 2 subarrays of 16 by 16. So therefore, I can create 2 beams. There you go, right? 2 beams. And as I keep increasing the frequency of operation, I can keep adding more and more beams. In this case, I also have 1,024 antenna elements. But in this case, I have decided to create 4 subarrays. So how many beams do I create, Lauro? 4, man. And then how many layers can I transmit? 4, right? I can create 1 layer, I can transmit 1 layer per beam. So I can do MIMO 4 by 4, right? In this case, I don't have cross-polarized antenna elements. As you can see, they're only 1 polarization, 45 degrees. So I can only create 1 beam. If I had the cross-polarized antenna elements in here, then I could create 2 beams. This will be at 45 degrees, right? Get the idea? If I have 1 subarray, I create 1 beam. The more antenna elements I have in a given subarray, right, the larger, the greater my gain, and the narrower my beam. Okay, so this is another example, 256 by 256. And in this case, I have 1,024 antenna elements, but rather than creating 4 subarrays, I decided to create 8 subarrays. In this case, they are 16 by 8. What's the advantage, man? Oh, the advantage here is that I will have 8 beams. What's the disadvantage? That they will be wider and with smaller gain, all right? So Well, I was going to try to explain to you the concept of multi-user MIMO. The concept of multi-user MIMO means that I have, in this case, let's say 4 subarrays, right? I explained to you what a subarray is. It's nothing else than a collection of antenna elements. How many antenna elements? It depends on your vendor. It depends on who is selling you the equipment, okay? So in this case, let us assume that we have 4 subarrays as the way we described it. Let's say like that, right? We have 4 subarrays. So since we have 4 subarrays, in the case of cross-polarized, there is a question from Esward. When we have cross-polarized elements like this, right? Let me make another picture for you really quick. So the answer is yes. The short answer is yes. So if I have one subarray like this, let's say I have 1, 2, 3, 4, 5, 6, 7, 8, 8 times 4, right? Like that. I can only create one beam, right? If I have, you got the idea. I can only create one beam. And this is going to be at 45 degrees like that, right? I just drew it horizontally. Now, what happens if I do cross-polarization, man? If you do cross-polarization, then you can create another beam. And this beam is going to be like this. At 90 degrees, not 45, 90 degrees, okay? So 4 transmit and 4 receive. So 4 transmit means that you have 4 transmitting antennas. You're probably using, in that case, it depends on what you do, Manish. So if you transmit one layer, right? Okay, so sorry, let me finish this idea. So anyway, so when you have cross-polarization, in this case, cross-polarization, so you can use layer 1 here in port 1, and you can use layer 2 in port 2, right? So 2 layers, right? So that's how we do MIMO 2x2. So the difference between 4T4R and MIMO 4x4 is that in MIMO 4x4, you have to have 4 ports, 4 subarrays or 4 antennas, and each antenna transmits a given layer. So you have the 4 layers in MIMO 4x4. They're different information. It is as if you were playing, as if one of your kids was playing football, and then you have you, your wife, your mom, and your dad, and all of you send a given message to your kid who's playing football, right? That will be MIMO 4x4. Each of them are saying a given message, completely different. If the kid is going to play is going to kick a penalty kick, and you go and say, kick it to the left of the goalie. Your wife says, kick it really hard. Your mom says, but don't miss it. And your father says, kick it with the left foot, right? So those are 4 layers, 4 antennas, 4 transmitting antennas. And in this case, your kid has 2 receiving antennas. So in that case, it will be 4x2. When you can use 4T4R, right? If to transmit the same information in the 4 transmit antennas, right? So in that case, it wouldn't be MIMO because it's the same layer in the 4 antennas. You're using just transmit diversity. All right, so let's go back to multi-user MIMO really quick. So in multi-user MIMO, what's going to happen, guys, is that this is going to be, this is going to be the sector, right? This is going to be my sector, just like in LTE. However, we are going to cover this sector with beams. In this case, the antenna is capable, the G0B is capable of transmitting 4 layers with 4 subarrays. But my receivers, in this case, user number 1 and user number 2. User number 1 is Alice in this case. This is Alice and Bob. So in this case, Alice only has a device that can receive with 2 antennas, right? 4x2. So the G0B says, oh, what I'm going to do is I'm going to be using 1 beam to transmit 1 layer to Alice, and I'm going to be using another subarray to transmit another beam to Alice. So in this case, Alice is receiving 2x2. Note that the G0B can transmit 4x4, right? But the G0B has decided, oh, I'm going to be using 2 beams for Alice, and also I'm going to be using 2 beams for Bob, right? So what's the advantage here, Lauro? The advantage here is that I am increasing my cell capacity. Now, note that in this case, both of the subscribers are receiving, let's say, resource blocks 10 to 20, and Bob is also receiving resource blocks 10 to 20 at the same time, but they are in different locations. So what am I doing, Lauro? Increasing my cell capacity. I'm reusing resources inside the same sector. What is this called? Multi-user MIMO. Also, this is also known as space division multiple access. Okay, what is a beam? All right, so in 5G, so the easiest way for you to understand a beam is spotlight. Just think about the spotlight. So, for example, guys, when you go to a concert, right? Let's say that this is the stage, and you have the drummer and the guitar player. All of them are there. The bass player, all that jazz. You can cover these. You can cover this stage with a given light, a giant light, right? But that's not really cool because I cannot do anything with it. All the resources that I'm using in that light are for everyone. They're shared. So for example, here the guitar player can say, hey, I don't want that light. Sorry, man, I have to cover you. It's the only thing I have. However, when you do beams, just think about spotlights. It means that you can cover your entire sector with spotlights of different colors. Right, so you can have green. And the most important thing is that you can reuse the resources in every beam. Right? A beam is just essentially a coverage created or an antenna radiation pattern which is narrower. Right? Right. You can also think of the laser pointer, the light. Very good. What is the characteristics of beam? How you differentiate it? Typically, if you use in 5G, you use in LTE, if you use a given antenna, right? Let's say that this is the sector that you want to cover. You will have to go and get an antenna with a given antenna radiation pattern that kind of covers your sector, right? The problem there is that all the users in that given cell are going to be receiving the same information, whether they want it or not, right? They're going to be covered by the same spotlight, by the same energy. I don't want that to happen. So you can think of a beam as an antenna which has an antenna radiation pattern that is very narrow. So for example, in this case, you can have 2 UEs. When I use a wide antenna radiation pattern, all of them receive the same information. So for example, if I wanted to send data to Alice, Alice would be very happy to receive this coverage, this radiation of this energy, right? But Bob would be very mad. He says, why are you sending this stuff to me? Yeah, I don't need it. So a beam is nothing else than a radiation pattern that only covers a narrower area, right? This is a narrow area. That's it. In this case, if I send energy to Alice, Bob will not be receiving it. Okay. Very good. So that's multi-user MIMO, guys, here. Multi-user MIMO, right? So how do we do this, guys? With massive MIMO. What's massive MIMO? Those cases where you have a large collection of subarrays, right? That's it, in short. How is it possible to transmit using the same frequency time resources? Oh, because they are in separated spaces. Assume that you have 2, what do you call those things? Assume that you talk to someone with a megaphone in this direction. Hello, Alice. Bob is not hearing that way. Hello, Alice. And to Bob, hi, Bob. I can speak to both of them at the same time. They won't be hearing anything. Alice won't be hearing what I'm telling Bob, and Bob won't be able to hear what I'm sending to Alice. That's the easiest way I can explain it to you. Okay, so really quick, guys. What happens, Lauro, when we compare the propagation characteristics in frequency range 1 versus frequency range 2? Okay, so there's going to be some differences, right? For those of you who have been working with LTE, UMTS, 1xEVDO, and all that jazz, we know that in frequency range 1, we have line of sight, reflections, diffraction, and scattering. All of these are actually very good in order to get coverage. However, in frequency range 2, frequencies of operation above 7 gigahertz, in particular, my 28 or 27 and my 39 gigahertz band, M261, M260, in those cases, the frequency of operation is really large and there's only line of sight. That is, in order for your 5G service, my mobile phone, this one, has to be pointing to the antenna, right? There has to be line of sight, otherwise I don't get coverage. In indoor environments, you get some reflections, right? And some scattering that may help you increase your signal. But for the most part, in outdoor environments, in frequency range 2, you need line of sight. Path losses. Well, we have path losses in frequency range 1, Lauro, yeah, but they're not as big as compared to the cases of frequency range 2, where we have more than 20 dB losses, right, as compared to the cases in frequency range 1. There is shadowing, Lauro, in frequency range 1. If a truck passes by, sometimes I see that, oh, I got one bar rather than 5. But in the case of frequency range 2, they're actually really bad. If you go and put your body in between you and the G0 beat, you will experience large losses, right? 20 dBs for humans and 40 dBs for walls. So indoor coverage is going to be very difficult, particularly in frequency range 2. If you have a window and the window is tinted, if you deploy it at 39 gigahertz, do not expect to see any coverage inside, okay? Even tinted windows, the film that you use for tinted windows will block your signal. Diffraction. We have diffraction in frequency range 1, man. There's no refraction in frequency range 2. The weather doesn't affect me, but if you live in the Northeast or in the Midwest, when it rains a lot and it snows a lot, you should expect your coverage to get very, very small, right? 7 dB per kilometer. Now, the channel, man, in LTE, my largest channel that I have in AWS is 20 megahertz. So my thermal noise, corresponds to that, to 20 megahertz. But in 5G, my carriers could be as large as 400 megahertz. Laura, but I don't have the spectrum. Yeah, but if you have 100 megahertz, you should be getting 7 dB more, right, of thermal noise because the carriers are huge. Okay, very good. All right.
So Laura, a quick question. There was one question about the idea of beamforming, is it more effective in TDD compared to FTD?
Oh, sorry, Ramki, what was it?
Beamforming in TDD, is it more effective in time division duplex because it's the same channel used in uplink and downlink?
There's no difference.
Good.
No difference at all. Has nothing to do with the duplexing scheme.
Excellent.
So this is
one more before you go. Can the same sector be configured for multi-user MIMO and single-user MIMO?
Yes, you can use them for anything. For example, guys, at one given time, it depends on where the users are, right? The G0B decides how to use the beams. So, for example, at a given time, if this is my G0B, I can have a user here, right? This is Alice. And provided I have enough beams, right, I can use Alice, I can cover Alice with 4 beams, right? 2 by 2, then I have 3 antennas, and then I have 4. Now, let us assume that this is my sector, right? That's my sector. And then let us assume that at another instant in time, this was time 1, then Alice is going to move here at time 2, right? So Alice moves there, and Bob is here. So at another instant of time, the genome beam might decide, oh, I'm not going to do 2 by 2 for Alice. I mean 4 by 4. I'm going to be using 2 by 2 for Alice. So this one was 4 by 4. Now I'm going to be using 2 by 2, and I'm going to be using the other beams for both. This is just a silly example, right? So yes, we can use them. We can use them or they could happen at a given time as well, right? At the same time. So the genome B says, I'm going to be using these beams for this guy now, 4 or 8. And then in other locations, I can do 2 for this guy and 2 for these guys. Remember that the genome B has subarrays. It might have up to 120 subarrays or 200 subarrays. It depends on the vendor. So I can use 4, right? 4 subarrays for 4 by 4 for this guy, 4 for 4 by 4 for this guy, 8 for 8 by 8 for this guy, and then I can do 2 for these, 2 for this. That's multi-user MIMO and single-user MIMO at the same time. Very good questions. Okay. Sorry if it feels that I'm rushing, but I'm trying to cover as much as possible. So this is another example of what I was telling you, right, guys? So here, this is not cross-polarized. This is just one single beam. So here we have 8 subarrays. So how many beams are we going to produce? 8. How many layers? 1 layer each of them. Right, remember, 1 layer each of them. 1 layer. Now I can also go and divide this into 4 beams, into 4 beams, 4 subarrays. So I have 256 antenna elements, but in this case I decided to have 8. In this case I decided to have 4. What's the difference, man? Oh, the difference here is that this one will have larger gain. Why, Lauro? Because we have more antenna elements, right? I have 8 by 8 in this case. So therefore the gain is larger and the beam width is smaller. Ah, smaller beams. Why, Lauro? Because you have more antenna elements. In this case, I have wider beams, they're wider, and the antenna gain is smaller. Okay, so hopefully this is making sense so far. And this is just a table that shows you what happens with the size of the antenna elements and why in frequency range 1, we don't have that many subarrays, right? Because look at the size of 1 gigahertz, one antenna element size in 1 gigahertz of operation. So this will be the size of my antenna element, 15 centimeters, like these guys. And they have to be separated by 15 centimeters. So you saw the size of the radome. Look at the size of the antennas when you drive. They're huge, right? The radomes. I cannot put many antenna elements there, Lauro. No, therefore your beams are going to be really wide, right? Because I only have four antenna elements. So my beams are 120 degrees or 60 or 70. They're big. Whereas when we go to, let's say, 32 gigahertz of operation, look at the size, guys. 5 millimeters, right? Awesome, right? So you can have a bazillion of antenna elements. Look, so you have a bazillion of antenna elements. Therefore, you can create really narrow beams with smaller gain. Now, guys, remember, they have more gain, but in frequency range 2, the frequencies of operation is very high. And as you saw, the propagation conditions are worse. And even though we have a lot of antenna gain, the signal doesn't travel too far, okay? All right, let's just go and tell you what happens with digital beamforming, analog beamforming, and hybrid beamforming. I'll try to cover as much as possible, guys. So here we go. What's digital beamforming, Lauro? Remember that the key was for beamforming to modify the amplitude and the phase so that we can direct the signal in a given direction. In the case of digital beamforming, we're going to do the digital beamforming in the digital domain. That is in the frequency domain, right? This is the time domain, the analog domain. What's the advantage of digital beamforming, Laura, or what happens? In the case of digital beamforming, we are modifying the amplitude and the phase of my symbols in the frequency domain, right? So here you have your digital to analog converter, your oscillator, your frequency of converters, and every antenna element every antenna element in here has to have, right, an amplifier. That's one of the main differences. They have an amplifier. Now, in this case, guys, since we are doing the modification of amplitude and phase in the frequency domain, I can create beams. I can create beams for every frequency of operation. For example, guys, let me show you. With digital beamforming, I can create a beam for Bob, right? If I send Bob resource blocks 10 to 20, I can create a beam in that direction because I'm modifying this in the frequency domain. So resource blocks 10 to 20, I'm going to create a beam that way. Whereas if I have Alice in the other direction here, and Alice is receiving resource blocks, actually in this case, Bob, resource blocks, let's say 30 to 40, then I can create another beam in that direction. And if I have another friend over here, I can create another beam in this direction, right? So this will be resource blocks 50 to 66. That's the advantage of digital beamforming. What's the disadvantage, Lauro? The disadvantage of digital beamforming is that it's really complex to create algorithms when the number of antenna elements is really large. Ah, so you're saying that digital beamforming is used in frequency range 1, Lauro? Yes. Why? Because the number of antenna elements is very small and the algorithms, right, wouldn't be so complicated. Now, on the contrary, when we do the analog beamforming, this is really good for frequency range 2, when the number of antenna elements is very large. So what's the difference here, Lauro? In the case of analog beamforming, I'm going to be doing the modification of amplitude and phase in the time domain. So what are you saying, man? In analog beamforming, for every symbol that I'm sending, right, I have to create only one beam for one given person. Get it, guys? In analog beamforming, since I cannot modify the amplitude and phases of my signals in the frequency domain, my G naught B can only create one given beam in a given direction, right? So this is Alice. So this is an analog beam. I can only create one beam in a given direction for all the frequencies, for my entire band. Whereas in digital beamforming, I can split my band and say one beam for resource blocks 1 to 10, 20 to 40, and 40 to 66. That's one of the main differences. All right. Is there a connection between network slicing and beamforming? Yes, you can probably say that, right? But let me think. Not really. It has to do more with bandwidth parts, right? That's another concept. In 5G, we use bandwidth parts, and we split my carrier into given bandwidth parts or chunks of resource blocks. Each resource block is going to be allocated to a given bandwidth part, to a given network slice, okay? So this is more or less the idea that I want you to get. Digital beamforming is really good for frequency range 1 because I have a small collection of antenna elements, and digital beamforming allows me to create beams in given directions for given frequencies, for given resource blocks. Analog beamforming only allows me to create one beam for all of my band. That's it. Now there's another algorithm called hybrid beamforming. In hybrid beamforming, I use the advantages of both. So I have my digital beamforming, and we make my digital beamforming algorithm think that I only have a few RF chains, right? Because I told you it's really good for a slow number of RF chains. By the way, guys, this is an RF chain, right? This is an RF chain. So we make the digital algorithm think that we only have a few of these chains. In reality is that we have more. Now each antenna, each RF chain also gets modified in the analog domain as well. So this is an algorithm that maybe not that many vendors have at the time. They're using digital and analog. I don't know of anyone who has been using hybrid beamforming so far, not like this. There's another way of doing hybrid beamforming that I'm not going to cover, but I haven't seen this. So think, guys, analog beamforming, frequency range 2 typically, and the beams are wider. Digital beamforming, frequency range 1. Okay, that's what I wanted you to get from this section. Now, I'm going to move into this one. Okay, so 64 by 64 massive MIMO means that you have 64 subarrays, right? If you could send, if your vendor supports sending one layer per beam, right? Meaning that you can have 64 layers, then you can do 64 by 64. Currently, the maximum is 8 by 8. Now, think about this, Manish. If I have 100 subarrays, ideally, I could produce 100 layers, yeah? 100 subarrays, 100 layers. However, currently, your vendors can only support sending 8 layers and the UE receiving 8 layers in frequency range 1. I haven't seen that, right? They only use 4 by 4. But ideally, if you could send 100 layers and if you have 100 subarrays, go ahead and do it, man. But, you know, in reality, it'll be 128 by 128 or 64 by 64, right? If you have the 64 subarrays and if you can send 64 layers, do it. But that technology doesn't exist yet. We are only all the way to 8 by 8, okay? All right, really quick. So beams in 5G, guys. In LTE, you only use one sector. Your antenna radiation patterns covers one sector. In 5G, depending on the frequency of operation, you can cover your entire sector with something called coverage beams or wide beams. If you are deploying 5G in frequencies smaller than 3 gigahertz, then the standard tells you that you can have up to 4, right? Up to 4 coverage beams. 4 coverage beams, right? And these beams get transmitted like a sprinkler. 1, 2, 3, 4. Every 20 milliseconds, 1, 2, 3, 4. Like a sprinkler, guys. If you deploy 5G in between 3 and 8 and 7 gigahertz, the standard tells you that you should cover your entire sector with up to 8 beams, right? So for example, here I told you up to 4. I've seen vendors doing only 1. The standard says you can use up to 4, but you know, you can do whatever you want. So I've seen vendors doing it with 1, and I've seen vendors covering the sector with 4. So it depends on their capabilities and their choices, right? So in this other example, in between 3 and 7, the standard says you should cover the sector, the LTE sector, right? In this case, with up to 8 coverage beams. I haven't seen this solution yet. I'm waiting for network operators to deploy in CBRS and see what they do. But you can cover with up to 8. You don't have to. If you don't have the 8 subarrays, you don't have to. You can do 4, you can do 2, you can do 1, right? Now, in frequency range 2, you should cover your sector with up to 64 coverage beams. You don't have to. For example, I have seen some vendors covering with 12, and I have seen other vendors covering with 32, and other ones with 56, and you know who you are, right? Now, these beams, my friends, are not horizontal, right? They could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Horizontal and vertical. These are known as coverage beams. Now, these coverage beams, guys, these coverage beams carry control information. They carry my synchronization signal block. That is my primary synchronization signal, my secondary synchronization signal, and also they carry my MIB, my master information block, which goes inside my PVCH. Okay? So In 5G, you're going to have something called coverage beams. I told you how many you can have, and they're typically analog, right? Coverage beams. And inside your coverage beams, you are going to have something called traffic beams, which are narrower. Could be or not narrower. These traffic beams actually carry user data, okay? So there you go. This is an example, guys, in which we have 8 coverage beams. 8 coverage beams, right? 8 coverage beams. Remember, my coverage beams carries my primary synchronization signal, my secondary synchronization signal, and my PVCH. Let me show you a picture really quick so you have an idea. And this synchronization, right? This is an example, guys, of one coverage beam right there, right? This is one beam in the time domain when it gets transmitted. What you see in here as the green resource elements, that's my primary synchronization signal. The blue one is my secondary synchronization signal. What you see in red is the PVCH or my MIB. And as you see, in this example, I'm showing you 4, 8, 16 beams, right, in the time domain. So this beam 0 goes there, beam 1 goes in here, 2, 3, 4, 5, 6, 7, 8, and then vertical. Those are called my coverage beams, and they transmit. They use 20 resource blocks, right? 20 resource blocks. And typically your vendors put these SSB beams or coverage beams in the middle of your carrier, okay? Do you like the sound effects? Yeah, this class includes everything. All right, so I get my phone, right? I get my phone, I switch it on. What does my phone do? It looks for the coverage beams. Lauro, how does the UE determine the beam number? What I showed you here, when you look at this stuff, right? You see these yellow lines that run horizontally? These are called demodulation reference signals, right there. Demodulation reference signals are masked with the beam number, right? So that's true for 8 beams. When you have 64, then the MIB carries 3 extra bits that allow the UE to identify the beam number. So in this case, this subscriber says, oh, I am in SSB number 8. How did you know that? Oh, because of the demodulation reference signals that came inside the PVCH block. So the UE knows in which beam it is, right? Now, now what happens next, Laura? What happens next with the RATCH? Oh, then the UE has to perform RATCH. And this is, I'm going to try to address the question earlier. The UE has to do RATCH, right? Because the E0B needs to know where you are. The E0B doesn't know where you are. You have to tell the G0B, right? But how do you tell the G0B? Via the RATCH. Cool. So in the uplink, I have to do RATCH. I already know in which beam, coverage beam I am. Remember, coverage beams only transmit control information. Right? In this case, the UE already knows the PCI by the primary and the secondary synchronization signal, and it also knows the master information block. Now the UE needs to perform RATCH. How does it do it, Lauro? Let us assume this case where we have 4 beams, 4 coverage beams. In this example, I am assuming, right, that these beams get transmitted every 20 milliseconds, right? 20 milliseconds, like this. So the G0B goes 4, it waits 20 milliseconds, waits 20 milliseconds, and then it does it again. But guess what? In this case, my subscriber, who happens to be my grandma, right? Grandma needs to go and tell the G0B in which beam it is. How does he do it? Well, grandma knows where the RATCH slot is going to happen in the uplink, okay? So every RATCH slot contains something called RATCH occasions. In this example, I'm showing you that there are 2 RATCH slots in 20 milliseconds, right? In 20 milliseconds, there are 2 RATCH slots. So grandma says there are 2 RATCH slots. Each RATCH slot contains a RATCH occasion. Since grandma says, I am in in beam number 3. Ah, cool, Grandma. Therefore, you should use Raj occasion number 3 in order to do random access request. So Grandma does random access request, right? And Grandma, by doing Raj in the random access request, in the Raj slot number 3, Grandma is telling implicitly the G0B that she is in coverage beam number 3. And answering your question, you do have to do Raj sequence index planning, Raj sequence index planning in frequency range 2 from scratch. It depends on how many preambles you have per beam. It depends on your vendor, but typically you will have to do it. You cannot do the LTE Raj sequence index planning. You have to redo it. Okay, so now we are there, guys. Now the G0B knows where Grandma is, in which SSB she is. Now remember, I told you, inside every coverage beam, we are going to have something called traffic beams. Traffic beams. So we know that Grandma is here, right? So I'm going to tell, the G0B is going to tell Grandma, Grandma, please listen. I know that you are in Sept number 2. Please listen to this beam who is identified by a given reference signal. This reference signal is called channel state information reference signal. I need you to tell me the RSRP, tell me the RSRP, and this is what this is layer 1, guys. This is not layer 3. This is layer 1. Fast measurement. Every 60 milliseconds, every 80 milliseconds. Please send me the RSRP of traffic beam number 4. Tell me the RSRP, and of course the beam number of traffic beam number 5, and tell me the RSRP of traffic beam, this is layer 1, guys, number 6. Because I need to know where you are. By comparing your RSRP, by comparing the RSRP of these beams, I know that you have moved from one traffic beam to another traffic beam. The G0B would configure the UEs, right, with these measurements, just like a measurement report in LTE for layer 3. These are layer 1 though. And the G0B might ask Grandma, Grandma, tell me the CQI of that given traffic beam, or tell me the PMI, right, that precoding matrix indicator. Tell me how many layers you can hear, right? Tell me the rank indicator, how many antennas can you distinguish? Tell me the layer 1 RSRP. Remember, this is really fast. And also, tell me the traffic beam number. This is my traffic beam number. And in some occasions, the G0B might also ask Grandma and tell me